Welcome to Homework Lib.
We are given that there are two equal charges positioned at two different points. So over here we have let's make a figure while we read the question, because that's really important. It will help us to reduce the direction. So L comma x coordinate is L, y coordinate is 0. It means it is on x axis, and it's over here L0, and the other point is at minus L0. That's symmetric over to the other side. That's minus L0. There are two equal charges over here. Let's represent the charge as well. This is Q. This is Q. All right. Determine the electric field as a function of y for points along the y-axis and show that the field is maximum at this particular point. So let's say we need to find the field, electric field somewhere at this point. So its coordinate is given by 0 comma y at any point on the y. So because of this, these two, we have to find the electric field. So magnitude is definitely going to be same because they are symmetrically positioned, and the distance between these two is going to be same. Let's call the distance as r, and we know that using the Pythagoras theorem, r square is nothing but L square plus y square. This is L and this is y. This is the value of r square. So the electric field. Now let's talk about the direction. So the direction due to q is going to be over here, and the direction due to that q is going to be over here. So let's call the value of the electric field as E, and we are going to make its components. So definitely, whenever we are going to make its components, the horizontal component Ex and the vertical component is Ey. Likewise, its horizontal component is Ex and its vertical component is going to add to Ey. So the horizontal components Ex and Ex is going to be cancelled, and the vertical component is going to add with each other. So the net electric field is going to be 2 times E of y. The net electric field is going to be 2 times E of y. E of y means the y component of the electric field. So E of y, what's going to be E of y? So for that, we need to work a little bit on the angles. So let's say if this is the angle theta, this means that uh, this angle is uh, let's try to work. This angle is also going to be theta, because why? Because this is a symmetric figure, so this is also going to be theta. So this will be 90, and due to the vertically opposite angle, this is also going to be theta. So the ey is going to be E sine theta, and the value of E is kq over r square, and the value of sine theta is going to be opposite over hypotenuse. Opposite is y, and the hypotenuse is r. So we have r over here once again. So it's only a matter of the substitution now. 2 times k is 9 times 10 raised to 9. Q remains the same. Y we have to find in terms of y over r cube, where r is square root of L square plus y square. So r cube is going to be L square plus y square raised to 3 over 2. So the final value, let's write it in terms of k. So that's going to be 2kqy over L square plus y square raised to 3 over 2. So this is the net electric field in terms of y at any point on the y-axis. So that answers part A. Part B talks about what is the maximum electric field is at this particular value of y. So that's where a little bit of calculus comes in, because the maximum is when its derivative is zero, as in we need to find the critical points. So for that, we are going to differentiate E with respect to y and equate it to zero. So this means that 2kq is a constant, it's going to come outside, and we are going to differentiate y over L square plus y square raised to 3 over 2 and equate this to 0. So this is anyway a constant is going to be merged to 0. And here we are going to use the quotient rule. So we have denominator square denominator, differentiation of numerator, differentiation of y is 1, minus numerator, which is y, and differentiation of denominator is going to be 3 over 2 times L square plus y square raised to 1 over 2. Then we go inside as per the chain rule. So the differentiation of L square is 0 and differentiation of y square is 2y. And this is going to be equal to 0. So this becomes L square plus y square. There's no significance of denominator because that's just gonna merge with 0 as per the cross multiplication. Minus this 2 and 2 is cancelled, and this y and y becomes y square. Minus y square times L square plus y square raised to 1 over 2 is equal to 0. So we can take L square plus y square raised to 1 over 2 as a common factor. So we are left with L square plus y square minus y square over here. And this is, let me check this once again. There's a 3 which we forgot to take over from here because this is the 3. So this should also come over here. So if when we take L square plus y square raised to 1 over 2 common, we are left with minus 3y square over here, and this is equal to 0. So this is possible only when either this is 0, which is not really possible. That's the sum of the perfect square. So in other words, L square plus y square minus 3y square must be 0, which means that L square is equal to 2y square, which in other words means that the value of y is nothing but L over root 2 with the plus minus sign. So these are the points where that's going to be these are the critical points. And to prove that, here we have a maxima. We are going to look at the sign of the derivative. We're going to look at the sign of the derivative. So minus L over, in fact, minus L over root 2 and L over root 2. So if we look at the sign of the derivative, that's going to be it's changing. Let's see. So it is changing. The derivative is over here, L square minus 2y square. So when it is less than this particular value, the value is going to be the sign is going to be taking any random value. Let's say minus L. So that's going to be negative, and it moves from negative to positive. And likewise over here as well, it moves from negative to positive. So we have a local minima at this point, which is exactly what we needed to local maxima at this point. Let's look at the sign once again. We have interpreted something wrong. So L square minus 2y square is the derivative. So now if we are going to place, let's say, y as 0, then the value of at L equal to 0, at y equal to 0, we are getting the differential sign as positive. So that's positive over here. So that swings from negative to positive and positive to negative over here. This means that there is a maxima at L over root 2. But what about minus L over root 2? So the minima at minus L over root 2 means its sign is negative, and the electric field is a vector quantity. So the negative value just means that the electric field is now pointing over to the other side. With the same magnitude, it's towards the other side. So since the magnitude is same but the direction has changed, so it is considering this minus E, let's say, as a minima. But in actual, this also is of the same magnitude. So we'll say the magnitude, we'll say that, or at both these points, that's going to be the magnitude is going to be maximum. Magnitude is maximum with different directions at minus L over root 2 and L over root 2. This proves that we have plus minus L over root 2 is a critical point of maximum value of the maximum value for the magnitude of the electric field. Thank you.